So to wrap up this very, very long section 9.1, or 10.1, excuse me, we're going to finish up our study of parametric equations by looking at doing calculus with parametric equations. From Calc 1, you'll remember that the slope of the line that's tangent to a graph at a particular point is simply the derivative, right? So that if I have a curve, y equals f of x, then the slope of that tangent line is dy dx. The question that we want to ask ourselves now is, how do we go about calculating that slope when our curve is defined not as a function of x, but in a parametric way? So what if curve is given by x equals some function f of t and g equals some function g of t? Then our slope or derivative dy dx, I'm so sorry, let's try that one more time. That was, I think I said y, but I wrote g there. It's an x equals and a y equals. So dy dx can actually be written as dy dt divided by dx dt. If you think about it, it kind of makes sense, because if you treat the derivatives as their quotient of differentials, right? We can't really do algebra, but we can think of it that way. We can imagine taking this dx dt from the denominator and rewriting it as multiplication by the reciprocal, dt dx. And then notice how those dt's would cancel out, and we would just have dy dx. So algebraically, it kind of makes sense. So here is the formal definition of that. When our curve is defined parametrically, the slope is still dy dx. And so we need to figure out how to find it, which we really just did. Dy dx, that derivative or slope, is found as dy dt divided by dx dt, as long as dx dt is non-zero. So let's do a couple problems like this. Here are my parametric equations, and my goal is to simply find dy dx at the point 1, 1. So dy dx we find as dy dt over dx dt, which would be, let's see, if I think of that y as t plus 1 to the negative first, then its derivative is going to be minus t plus 1 to the negative second. And my chain rule there just gives me a times 1, so I won't even bother writing it. And at the bottom, dx dt is going to be e to the 2t, and the chain rule there will give me a 2. So I could really write that as negative 1 over 2e to the 2t times that t plus 1 squared. All right, so I've got my derivative. I now need to actually find the value of the derivative at the point 1, 1. And here's where we have to kind of take stock again. My derivative is now a function of t, and the points that I was given are x and y. So I'm going to have to use that x and y to figure out t. My first equation, x equals e to the 2t. If I plug in x equals 1 and take the natural log of both sides, I would have 0 equals 2t or just t equals 0. When you only get one solution for t, it better be right, but it's not a bad idea to check. So this was my x equation. I can kind of check in the y equation. Y equals 1 over t plus 1. My y value is 1. And we were projecting the t was 0. And notice that 1 is equal to 1 over 1, so it checks. So we're going to go with t equals 0 here. I'll plug that 0 in for t in my derivative equation. So that'll become e to the 0 times 0 plus 1 squared. And let's see, e to the 0 is 1, 1 squared is 1, so that denominator is really just 2. And the derivative turns out to be negative 1/2. All right, the next problem or two, we'll look at the derivative as that slope application. So in example 2, we've got a new curve, and we've got our parametric equations for the curve given. And the first thing I'd like to do is find the slope of the tangent line at the point 5, negative 2. Well, first of all, we know that m is dy dx. And we are now finding that we calculate that as dy dt divided by dx dt. And in this case, our dy dt would be 6t squared. And our dx dt would be 2t plus 4. Same deal. I'm not given the t value to plug in here. Instead, I'm given the x and the y. So we'll use those to solve for t. My x equation would say 5 equals t squared plus 4t. And it's not horrible, but it's a quadratic equation to solve. Let me write the y equation as well. Y says 2t cubed minus 4 equals our y value of negative 2. That one's actually a little easier for me to solve, so I'm going to solve that one first. 2t cubed equals 2. T cubed equals 1. So t equals 1. And we're just going to double check, make sure that works in the x equation. And of course it does. So it looks like t equals 1 is what I want to plug in this time. So putting the 1 in for t, it's going to give me 6 on top and 6 on the bottom for a slope of 1. All right, part B. This time I want to find the actual equation of the tangent line, but I want to find it in parametric form. So we know our slope is 1. I'm going to think of that as 1 over 1, b over a. And we also know that a point on the line is this given point, 5, negative 2. So I can use that as the x naught and the y naught. And then, just because we haven't looked at it for a little bit, I'll remind you, x equals at plus x naught, and y equals bt plus y naught. So in this case, our equations become x equals 1t plus 5, and y equals 1t minus 2. Okay, last part of this problem just asks us to sketch the tangent line. The graph of the actual parametric function is provided. This is something, again, you can generate easily enough with a calculator or with Desmos. And we were looking at the equation of the tangent line at 5, -2. Would be right there. And it was a line with slope 1, so I'm just going to use the slope of 1 to sketch it. If I go over 1, I go up 1. Over 1, up 1. There's my tangent line. All right, one more tangent line problem. This time, my curve again is defined parametrically as x equals 3 cosine t, y equals 5 sine t. Notice with the cosine and the sine, I don't have the same multiplier, so this is going to be an ellipse. I would like to find the slope of the tangent line at t equal pi over 2 seconds. So again, slope dy dx. For parametric equations, calculate that as dy dt divided by dx dt. dy dt is going to be 5 cosine t and dx dt -3 sine t. This time, I don't have to work quite so hard because I was actually given the t value to plug in. So we'll just go ahead and do that. I have 5 cos pi over 2 divided by -3 sine pi over 2. Cosine of pi over 2 is 0. And sine pi over 2 is 1. So I actually just have 0 over -3 for a final slope of 0. All right, the next thing that I need is parametric equations for the tangent line at t equal pi over 2. I have my slope, which is 0. I'll think of that as 0 over 1. So once again, I have the b and the a. And then I need a point. Last time the point was given. This time I'm actually going to have to work just a little bit harder for it. Since I know the t value, I could plug them in up here to get the x and the y. So for x, I'll go with 3 cosine pi halves. Cosine pi halves is 0, so that's 0. And for y, we'll go with 5 sine pi halves. Sine of pi halves is 1, so that's just going to be 5. So that's my point, x naught, y naught. All right, that's everything we need to write the equations for the tangent line. X equals 1t plus 0, and y equals 0t plus 5, or simply x equals t, y equals 5. All right, then once again, we're just going to sketch the tangent line on the graph of the function. This one's not too tough. Our point of tangency here that we just figured out was 0, 5. So our point of tangency is right up here at the top of the ellipse. And just visually, you can see that that tangent line has to be horizontal, but we did find a slope of 0. So it is absolutely a horizontal line. Notice that with that horizontal line, the parametric equations effectively say y has to stay 5 all the time, and x can be anything, any t value. So that gives you the whole line. So, derivatives can be done for parametric functions, and furthermore, they can be used to find slopes and equations of tangent lines. If we could do a derivative, it stands to reason we could also do a second derivative. And so we'll look at that over here on this next page. So, since dy dx is going to end up being a function of t, we can actually use the theorem twice to find the higher order derivatives. For the second derivative of y with respect to x, we would have the derivative of the first derivative, which is going to be d dt of the first derivative over dx dt. Again, notice if I were to invert and multiply, the dt's would cancel, and I just have the derivative of the first derivative with respect to x. Let's try a couple of second derivatives. Here's my parametric equations. X equals 3t minus 5, and y equals the square root of t. And first, I just want that second derivative. Of course, I'll have to get the first derivative first. So I'll start with dy dx. Which is dy dt over dx dt. dy dt would be a 1/2 t to the negative 1/2, and dx dt would be 3. Or I could write that as 1/6 t to the negative 1/2. All right, ready for our second derivative. It is the derivative of the first derivative divided by dx dt. I have my first derivative right here, so taking the derivative of that is going to give me negative 1/12 t to the negative 3/2. On the bottom, I have dx dt again, and that's just back to the original x. So that's going to be 3. And so I end up with negative 1/36 t to the negative 3/2 for my second derivative. All right, part B asks us to evaluate that second derivative for t equals 1. And so, of course, just plugging 1 into this, I'd have negative 1/36 times 1 to the negative 3/2. 1 to any power is still 1. So I'm just going to get negative 1/36. And then finally, and there's a typo on this one, we'll fix that before we do the problem. It says to evaluate the second derivative at the point 1, 2. That point is actually not on the graph. There should have been a square root on that too. So please redo that. It should be the point 1 square root 2. All right, unlike up here where I already knew the t value and all I had to do was plug it in, this time I know an x and a y. So I'll have to use those to get t in order to plug into my second derivative. So here's x, here's y, and it's back up at the top, but I'll just remind you the x equation. X equals 3t minus 5. So if x is 1, I'm going to get 2 for t. Our y equation, again back up at the top of the problem, was y equals the square root of t. So if I put the square root of 2 for y, Again, if you just square both sides, it's clear that t is 2. So I'm now going to evaluate my second derivative for t equal 2. And that's going to give me negative 1/36 times 2 to the negative 3/2, which doesn't turn out to be a particularly nice number. If you plug that in a calculator, you get about negative 0.0098 for your second derivative. All right, so there's a couple of derivative issues with parametric equations. Let's also look at an integration issue. It doesn't exactly make sense to integrate the parametric function itself, but there's an application of integration for parametric equations that we do want to talk about. If we're given a curve in parametric form, could we find the arc length? Remember, we already looked at how to find the arc length for a function given as y equals f of x. We did that, I think, in Unit 1 of the course. Now I want to say, what if I'm given my function parametrically instead? How do I find the arc length? So as long as I've got a smooth curve, and c doesn't intersect itself on the interval, except maybe at the endpoints, then I can find the arc length of that curve over the given interval by integrating from a to b the t values, the square root of dx dt squared plus dy dt squared dt. And here that same thing is again in the f and g notation. Same thing. One note, we saw last time that sometimes based on the interval of t values that you're given, we have curves that are traced out more than once. Maybe we go one direction, then we come back the other direction, or maybe we go around a circle 2 or 3 times, right? When you're applying your arc length formula, it's important to be sure that the curve is traced out just once over the interval of integration. Otherwise, we're going to get some inaccuracies. All right, here we go. Example 5. I would like the length of the curve defined parametrically by the x and y equations here for t goes from negative 1 to 0. So our arc length s is the integral, and I'm given the t values, so I'll just go ahead and plug those in from negative 1 to 0 of the square root of dx dt squared. That would be 2t squared plus dy dt squared. That'll be 12t squared squared integrated dt. Now, as we saw earlier, oftentimes arc length formulas are particularly messy to evaluate by hand. This one's technically doable if you kind of factor out a t squared, but I'm not going to hold you responsible for integrating these by hand. Once you have them set up, perfectly fine to just set that integral right into the calculator, and if you do, you're going to get about 4.15 for that arc length. All right. One more arc length problem. This is a special kind of curve called an epicycloid. Here's how it's formed. If we take a circle of radius 1 and we roll it around the circumference of a larger circle of radius 4, kind of like the diagram shows here, then a point on the smaller circle will trace out this path called the epicycloid. My goal is to find the distance traveled by that point that was originally right there and is rolled around the circle as it travels and traced out that epicycloid. That distance, of course, is just going to be the arc length of the epicycloid. So it may look like a complex problem, but it's nothing more than an application of the arc length formula. Right? One thing we may want to address here, because we did see before that we have to be a little bit careful as far as tracing over themselves and things like that, especially with circular functions. Let's make sure we know what t-values it will take to trace that whole epicycloid once. So in my y equals, I've actually already got the x and the y in there. This is that 5 cos t minus cos 5t is cut off, of course. And here's the y, 5 sine t, and that says minus sine 5t. And in my window, right now I went 0 to 2 pi, since typically circular functions are completely traced out over the t-values in the interval 0 to 2 pi. I've got my x and y set to -8 to 8 on both axes, and I'm going to graph. Well, it definitely looks like the whole epicycloid got traced out. We want to make sure that it wasn't traced out more than once. And here's an easy way to do that. Just hit your trace key. Notice that in addition to the x and the y, they also give you the t-value on the trace. And if I just start tracing my way around this curve, she looks like I'm at about pi here, but I want to go all the way around until I get back to 4, 0 again. There it is, back at 4, 0. Notice that t-value does indeed look like 2 pi. So I'm pretty comfortable saying that when I do my arc length integral, I would like to go from 0 to 2 pi. I then need the square root of dx dt squared. Dx dt, -5 sine t. That'll be minus a negative, so plus 5 sine 5t. Little chain rule in there, right? And that gets squared. Plus the y derivative, dy dt. That'll be 5 cosine t minus 5 cos 5t. Squaring that, dt. And again, a really ugly integral. If I was going to try to do it by hand, I suppose I'd square everything out and see if anything good happens, but we don't need to do that. Perfectly acceptable to type this in the calculator. When I did that, I got the rather surprising answer of just the whole number 40 as the length of that whole epicycloid. All right, so those are a few calculus applications for our parametric equations, and this does finally bring us to the end of section 10.1.